Digital afterlife. Can data become a soul? The quest for immortality has evolved from ancient alchemical pursuits into a sophisticated technological endeavor that promises to transform death itself. As artificial intelligence systems grow increasingly sophisticated and our understanding of the brain reaches unprecedented depth, a provocative question emerges from the intersection of neuroscience and computer science. Can human consciousness, that ineffable essence of who we are, be reduced to data and preserved beyond biological death? The concept of digital afterlife, encompassing mind uploading, consciousness transfer, and virtual immortality, represents perhaps the most audacious application of technology to the human condition. This emerging field stands at the crossroads of cutting-edge science and age-old philosophical questions about the nature of consciousness, identity, and what it truly means to be human. While science fiction has long explored these themes, recent advances in brain mapping, artificial intelligence, and computational power have transformed digital afterlife from speculative fantasy into a legitimate area of scientific research. Yet the gap between current capabilities and the grand vision of uploading human minds remains vast, raising fundamental questions about whether such technological transcendence is scientifically feasible or merely an elaborate digital mirage. The scientific foundation, mapping the mind's architecture. At the heart of digital afterlife lies the Connectome, a comprehensive map of neural connections in the brain that researchers believe contains the essence of human consciousness. The human brain contains approximately 86 billion neurons, each forming thousands of synapses with other neurons, creating a network of staggering complexity. These connections, totaling over 150 million synapses even in a fragment of brain tissue the size of half a grain of rice, create the neural circuits that underpin everything from basic motor functions to complex thoughts and feelings. Recent breakthroughs in brain mapping have provided unprecedented insights into this neural architecture. Google researchers' Connectomics team, marking 10 years of research, recently published a reconstruction of a small piece of human brain tissue that requires 1.4 petabytes, 1.4 million gigabytes, to encode. This fragment includes about 57,000 cells and reveals previously unknown neural structures, demonstrating both the remarkable progress in brain mapping technology and the extraordinary scale of the challenge ahead. The Human Connectome project, launched by the National Institutes of Health, represents the most ambitious attempt to systematically map brain connections in healthy adults. By combining multiple brain imaging technologies, including diffusion-weighted magnetic resonance imaging and functional MRI, researchers are creating detailed maps of how different brain regions connect and communicate. This work has already revealed that brain circuitry is organized more like Manhattan's orderly street grid than London's chaotic tangle of roadways, suggesting underlying organizational principles that could inform digital reconstruction efforts. However, the technical challenges remain formidable. Current brain mapping techniques can trace major fiber bundles and identify functional networks, but they cannot capture the nanometer-scale details of individual synapses across entire brains. Achieving the resolution necessary for complete neural reconstruction would require advances in imaging technology that may be decades away. Moreover, the human brain's connectome is hundreds of thousands of times larger than the human genome, representing a data processing challenge of unprecedented scope. Contemporary research approaches these limitations through graduated strategies. Scientists have successfully mapped the connectomes of simpler organisms, the 302 neurons of the nematode C. elegans in 1986, and more recently, 25,000 neurons in the fruit fly Drosophila melanogaster. Each step up in complexity reveals new challenges. Mapping mouse connectomes would require reconstructing over 100,000 neurons, and current imaging technology cannot achieve this scale with sufficient precision. The consciousness conundrum, from neurons to experience. The technical challenges of brain mapping pale in comparison to the fundamental philosophical problem that digital afterlife confronts: the nature of consciousness itself. Even if we could perfectly map and simulate every neural connection, would the resulting digital system actually experience consciousness? Or would it merely be an elaborate computational mimic devoid of inner life? This question strikes at the heart of the mind-body problem that has puzzled philosophers for centuries. Modern neuroscience generally embraces physicalism, the view that consciousness emerges from the brain's physical processes and could, in theory, be replicated in digital form. Many neuroscientists believe that the human mind is largely an emergent property of the information processing of its neuronal network, and that important functions performed by the mind, such as learning, memory, and consciousness, are due to purely physical and electrochemical processes in the brain. Yet this materialist view faces significant challenges. Human consciousness encompasses subjective experiences, what philosophers call qualia, that seem irreducible to mere information processing. The redness of red, the pain of injury, the joy of discovery, these experiences have a qualitative dimension that may not survive translation into digital code. As philosopher Rebecca Goldstein notes, The fact that some hunks of matter have an inner life is unlike any other properties of matter we have yet encountered. The implications for digital afterlife are profound and unsettling. Even if we could create perfect neural simulations, the resulting digital beings might be philosophical zombies, entities that behave as if conscious but lack any inner experience. From an external perspective, such beings would be indistinguishable from conscious entities, responding appropriately to stimuli and engaging in complex behaviors. But the crucial question remains: would there be something it is like to be such a digital entity? This uncertainty creates what some researchers call the copy problem. The question of whether digital mind uploading would preserve continuous personal identity or merely create a copy while the original consciousness perishes. Philosopher Susan Schneider argues that uploading would probably result in the death of the original person's brain, while only outside observers can maintain the illusion of the original person still being alive. The digital version might carry all memories and personality traits, but it could represent a fundamentally different being sharing the original's identity only through external appearance. Technical deep dive: the architecture of artificial consciousness. Understanding the feasibility of digital afterlife requires examining the computational requirements for simulating conscious experience. The human brain operates at extraordinary efficiency, using no more power than a dim incandescent light bulb, yet accomplishing feats that challenge our most advanced artificial systems. Replicating this performance digitally would require unprecedented computational resources and novel approaches to information processing. Current approaches to brain simulation fall into several categories, each with distinct advantages and limitations. Whole brain emulation attempts to create comprehensive digital replicas of entire brains, capturing both structure and dynamics at sufficient resolution to preserve conscious experience. This approach requires detailed mapping of neural connectivity, accurate modeling of cellular behavior, and massive computational power to simulate billions of neurons in real time. Alternative approaches focus on gradual replacement rather than wholesale uploading. These strategies would involve substituting brain components with synthetic equivalents over time until the entire brain becomes artificial. Some working examples already exist. Hippocampal prosthetics have been shown to improve visual memory in humans, while brain-computer interfaces like stentrodes help paralyzed patients control computers with their thoughts. These devices suggest that biological digital hybrid systems may provide a more practical pathway toward digital consciousness than sudden wholesale uploading. The computational requirements for brain simulation are staggering. Even simplified models require enormous processing power. Simulating the visual cortex alone demands supercomputer-class resources, and scaling to full brain simulation pushes beyond current technological limits. Moreover, brain simulation faces the challenge of real-time operation. Conscious experience occurs in biological time, requiring digital systems to process information at the speed of neural activity. Advanced artificial intelligence offers potential solutions through more efficient processing architectures. Machine learning systems have achieved remarkable success in pattern recognition and decision-making, suggesting that conscious-like behavior might emerge from properly designed artificial networks. However, current AI systems, despite their impressive capabilities, show little evidence of genuine consciousness or subjective experience. They excel at specific tasks but lack the integrated, self-aware quality that characterizes human consciousness. The timing question adds another layer of complexity. Computer scientist Ray Kurzweil predicts that humans will achieve digital immortality as early as 2045, while other experts suggest that even basic whole brain emulation may require 60 years or more. These wildly divergent timelines reflect the fundamental uncertainty about whether digital consciousness represents an engineering challenge awaiting better technology or a conceptual impossibility that no amount of computational power can resolve. Case study: the limits of current brain-computer interfaces. Contemporary brain-computer interface research provides a valuable window into both the promise and limitations of neural technology. Companies like Neuralink, despite generating significant controversy, have demonstrated remarkable capabilities in direct neural communication. Their systems can decode motor intentions from brain signals, allowing paralyzed patients to control external devices with thought alone. However, these systems also illustrate the enormous gap between current capabilities and the requirements for consciousness uploading. Current brain-computer interfaces operate through relatively crude signal extraction, typically monitoring the electrical activity of thousands of neurons without distinguishing individual cellular contributions. While sufficient for motor control applications, this resolution falls far short of the detailed neural monitoring that consciousness uploading would require. True mind uploading would need to capture not just aggregate neural activity but the precise firing patterns of individual neurons and their complex interactions. The invasive nature of high-resolution neural interfaces presents additional challenges. Achieving the resolution necessary for consciousness uploading would require thousands or millions of recording electrodes distributed throughout the brain, a technological feat that current surgical techniques cannot accomplish safely. Non-invasive alternatives like functional MRI provide excellent spatial and temporal resolution but cannot capture the nanometer scale details of synaptic activity that may be crucial for consciousness. Moreover, current interfaces face significant stability issues. Implanted electrodes often degrade over time due to immune responses and mechanical stress, requiring replacement or adjustment. A system designed to preserve consciousness would need to operate reliably for decades or centuries, a durability standard far beyond current capabilities. The experience of patients using brain-computer interfaces also reveals important insights about the relationship between neural activity and conscious experience. While users can learn to control external devices through thought alone, they report that the process feels artificial and requires conscious effort rather than the effortless integration of normal motor control. This suggests that truly seamless brain-computer integration may require understanding and replicating not just neural signals but the subjective experience of intentional action.